we're going to do a quick overview and then go into some potential applications. So we're going to start just by talking about the most common type of fuel cell, which is a polymer electrolyte membrane fuel cell, or PEM fuel cell. And fuel cells are categorized depending on the type of electrolyte used. In this case, most often this is platinum right here. So you've got your anode, your electrolyte, and your cathode. And your fuel entering and exiting is usually hydrogen, and air comes in and out on this side. So what happens is the hydrogen will enter the anode of the fuel cell and pass through this membrane, which is usually platinum, which is a proton carrier but an electron barrier. So it acts as a catalyst to oxidize the hydrogen. So the hydrogen comes through here and becomes a proton, and then this electron is forced to go through an external circuit where it can power some kind of load, and then the electron rejoins the proton and combines with the oxygen in this air intake and forms water. So the great thing about fuel cells is it's really clean energy. It just comes from hydrogen, and the only byproduct is water. So now some applications.
So the first application that we will discuss is using this type of energy generation method to power homes in what's called a combined heat and power system, or a CHP. So rather than using power generated by centralized power plants, as you can see in this diagram above, having an on-site or home fuel cell has proven to be a cleaner, cheaper, and more efficient method of energy generation. So an example of this fuel cell is shown in this picture here. Now what's beneficial is, in addition to electrical generation, a byproduct of this process is also heat, which can be used to heat the home spatially or to heat water in the home. So shown in this graph below, and as we mentioned before, the usage of fuel cells cuts CO2 emissions as well as operating costs. And in the graph you can see on the left side here, just 1 kilowatt of solid oxide fuel cell has a greater carbon dioxide savings per kilowatt capacity than, for example, a 1 kilowatt Rankine cycle or even a 5 kilowatt gas engine. Now, as I was mentioning before, in this diagram, the blue segment shows what it would be like if energy were generated by a fuel cell. So since the fuel cell uses energy straight from the source, cuts out the middleman, and utilizes the otherwise wasted heat, shown as 58% loss in a centralized system, and it utilizes that heat to heat the home. So in this diagram is just the process similar to a thermodynamic process that we've studied throughout the semester. At the beginning, on the left side, the fuel enters the system through the fuel processor, which converts natural gas, for example, into hydrogen and carbon dioxide. Hydrogen is, like we mentioned, one of the inputs into a fuel cell. Next, it enters the fuel cell itself, where, as we described before, the hydrogen and oxygen from the atmosphere combine to produce heat, electricity, and water. Next, the inverter converts output DC power to AC power to use in the home to power electronics, and excess power is sent back to the grid. The heat recovery system below simply improves performance of the fuel cell and is what distinguishes it as a combined heating and power system. The boiler provides a higher thermal load in series with this fuel cell, to maximize the heat output into the house or into the water that could be heated. And then shown in the bottom right is the hot water storage, like I mentioned, which is a way to make use of this excess heat, um, as well as some of the water being recycled back into the beginning of the cycle. The components I did not mention are there simply to ensure stable, safe, and long-term operation. Now, this image on the right is currently the only certified home fuel cell product on the UK market. It's manufactured by a company called Ceramic Fuel Cells. The name of this unit is the Blue Gen Fuel Unit. And what the company is aiming to do is develop a virtual grid, uh, basically by combining several of these fuel cells in homes, as well as managing the power generation remotely based on the power demand of each individual home. In turn, enough combined units would act as several centralized power plants. However, they would be acting with much higher electrical efficiencies, as I mentioned in the previous slide. Furthermore, the lack of moving parts in these fuel cells creates a minimal demand for maintenance work, which is ideal for a home. Uh, Actually, the only maintenance work is required by the auxiliary components of the system and not the fuel cell itself. However, the lack of standard industry prices for the fuel cell um, makes this system impractical for now. However, this is only because of the maturity of the technology.
So, when talking about electric cars, one of the common downfalls is range from the battery packs. So one of the things they've done is create hybrid vehicles that have an internal combustion engine um, that you can switch over to if you have a long trip. One of the great things about fuel cells is they actually can replace the internal combustion engine when a larger battery pack isn't practical. So, one thing we want to look at is the maximum efficiency. So fuel cells actually have a much higher maximum efficiency, theoretically, than an internal combustion engine. So, and the way they calculate is a little bit different. So they use the useful output energy divided by the change in stored chemical energy, which again comes from that hydrogen losing an electron, going through that membrane, and then rejoining with the electron it lost and combining with the air, which has oxygen in it, and producing water. So here you can see some values that research we've found on these fuel cells, and we've determined that the maximum theoretical efficiency is 83% versus an efficiency of 58% for internal combustion engines. And in reality, it's actually more about 25% efficiency for combustion engines and 40 to 60% for fuel cells. So here we're actually looking at a fuel cell stack, which is just basically a whole bunch of fuel cells in series, which is how we use them in cars. So this here is actually the fuel cell stack that you might find in that Honda. And basically all it's doing is combining each of these. So one fuel cell here may only produce about a volt. So you can actually stack, 80, hundreds of these and get the voltage that you need out of them. So that's just one application for these is in cars. And there are some limitations with it. For example, just getting the fuel is one limitation because it's very expensive to create this hydrogen. And also there really is a lack of fuel delivery infrastructure because everything's built around diesel and petrol. So it may take decades for this to ever get put into place. And here are some of our works cited.
Thank you very much.